T gets larger, therefore you get less efficient, but you do pay a volume penalty. And on a campus level, that may not matter. On a residential level, it probably would. So how big is that penalty?
In terms of volumetric storage, I'd guess 2, 3, 4 to 1, depending on what temperatures you're using. For instance, we use 10 million gallons of cold water storage in our system that previously was probably about 3 or 4 million total gallons in the ice tank. So it could be 2, 3 times.
Thank you.
Great. Chris?
A quick question for Joe. You talked mainly about university central energy plants. And is there a reason that we couldn't think about the same kind of basic philosophy all the way from neighborhoods up to big cities?
Yeah, it was district energy centric because of time. But if you think about it, you can push it down to commercial and even residential. So any of you that live in an area where you have your air conditioning on in summer and you turn hot water on to make hot water for your bath or your cooking in the kitchen or your showers, while your air conditioner is exhausting a similar level of heat out the back, you can see that it's possible at the residential. Now, what the overlap is and how much you'd size a little hot water and cold water tank for a house, I don't know. It'd be a great study to find out, though. You could also connect all those houses with a district energy system and get even more benefit that way.
I can't resist adding a brief remark, because I noticed on ASU's campus, if they chill at night, it's actually costing less energy in spite of the storage penalty.
Yes.
Because the delta T is significantly smaller.
Mm-hmm. Yeah, it's another good point about thermal storage, especially for cooling, is you can move it to lower outside temperatures and get more efficiency out of the process.
Mm-hmm. Yep.
Great. I didn't see you, Matt.
I have a question for Tom and a question for Jack. Tom, it sounds like there's a lot of energy available in cars, but it seems like the confidence of that resource being available is a challenge, or is one big challenge. Do you have any idea of how confident you can be with how much resource is available?
Yeah, so what I sort of talked about, I mean, the curve that sort of shows that, people leave during the day and do all this kind of stuff. I mean, we've done some studies where we can say, okay, with travel survey data, we can understand how people actually drive their cars and where they're parked and all this kind of stuff like that. And so we can go in and say, if you have one vehicle, it will be, sort of directly dispatchable or something at something like 60% reliability, which is far too unreliable. If you have two vehicles, then you do the sort of math or whatever, and it comes out 85% reliable. If you have three vehicles or whatever, 3.5 or 4 vehicles, then you can get to 99% reliable to be able to dispatch one of those at a particular time. So you sort of, at least as order of magnitude, and obviously that does, those are sort of calculations that you do, assuming that these are all uncorrelated and yada, 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 right? But at least order of magnitude, if you can aggregate 4 vehicles, or a 4x of any particular vehicle, then you can actually generate reliable
there you end up cutting
services.
into the amount of energy available, so you have to divide by 4.
Yeah, divide it by 4, divide your money by 4, exactly. So this is the challenge. But I think that's what you state is the key point, because if it's a home energy storage device that's plugged into the grid and bolted to your garage floor, then you don't have to pay that penalty. But the downside is presumably it has less, perhaps primary value to you as a consumer, because you're not transporting yourself with it and saving money and doing all that kind of stuff with it.
And then Jack, I have a question about electricity costs. So my understanding of electrolysis is that electricity costs are about 60 to 70% of the costs of hydrogen. And
yeah,
so
it's one of the quibbles that I have with some of the previous studies that assume a very low cost of electricity. Even some of the stuff that we've done, it doesn't become cost effective to make hydrogen unless electricity prices are fairly low. And you can assume that, for example, if you're providing other grid services, like using otherwise curtailed electricity or dynamically dispatching and getting paid for ramping up, ramping down, things like that. Maybe given those things, you can get lower electricity prices and as a result produce hydrogen cost effectively. But you're correct. Most of the cost of the hydrogen is associated with purchasing the electricity.
Right, and then if just some simple calculations I've done, just that cost alone is factor of 2 or 3 higher than hydrogen costs today. And
It is because natural gas is so cheap and SMR is pretty good at making it, okay? And I agree with you. However, you have these, I want to focus your attention a little bit on these synergistic ways of making it. So for example, if you can make it with heat that you have available from somewhere else, from a nuclear power plant, from some other waste heat stream that you have, even concentrated solar thermal power could be used with the SOEC technology to actually make some of that hydrogen from heat, and it could pretty dramatically improve those numbers.
2 quick questions for Joe. So building from what you just were describing, as you go from the scale of a Stanford campus to applying thermal storage to district heating, do you think you're looking at all economies of scales, or are there some substantial gotchas or diseconomies there?
We don't see any economies of scale penalties going downwards. Heat pumps have been available on small scale for a long time, so we had to work with companies to build ones big enough for a big system. So I think going larger, you have to get the equipment. I don't think there's an energy or cost penalty. I just think the larger equipment to go even bigger scale than, say, a university, you'd either have to have more pieces of equipment, like if you're doing district energy for the whole city of San Francisco, you might need a fleet of 20 2,500 ton heat pumps, or 10 4,000 heat pumps. You wouldn't be able to get a 20 or 30,000 ton heat pump from a manufacturer right now.
My second quick question was, there was a lot of conversation yesterday about the importance of pilot projects to sharpen where we need to have innovation moving forward. I'd love to hear, as you encountered barriers in developing the Stanford system, what were the key factors for overcoming them? And having done it at Stanford, to what degree have you found traction at the city scale in enabling other people to see ways to make it happen?
So we didn't have, honestly, a whole lot of, I'll say, barriers. There was just the due diligence to model and prove the system would work, and we had very receptive faculty and leadership that once you had very thorough proof that was very transparent, peer-reviewed, it was an easy sell because it saves hundreds of millions of dollars over the best cogen or any of the systems. So the university didn't have to make a choice to go green and spend more, or to not be as green and save money. It was a win-win. Interesting, we've had thousands of visitors from all over the world tour the plant, and including some other universities that their infrastructure is now at a scale where it's time to renew it, and they have a choice to, say, put in a cogen plant or put in some other plant or system like this. And we've helped them model a system like this and shown that it would work. But the barriers are resistance to change, resistance to the scale of the work. You have to put in a hot water system. Almost all these district energy systems use steam. And so the concept of, gee, I have to lay in a whole new piping system to 100 buildings and change the building point of connection, that's daunting for a lot of places. It wasn't daunting for Stanford leadership, and it only took 2.5 years, actually. The faculty could tell you how much disruption there was. But we decided to just pull the Band-Aid off and do it, and it's done. In less than 5 years, we're at 2/3 greenhouse gas reduction with an easy path to 80% if we go renewable. It also saves a lot of water, 20% savings in our total campus water supply, because most places use evaporative cooling to reject heat, and that's often a fresh water supply, not reclaimed. So there's just substantial money and sustainability savings, but it's a complete transformation. A lot of people just don't want to do the work and are putting it off for the next 30 years and throwing a cogen plant in or something. So I think it's philosophical is the biggest barrier.
Sorry, I just wanted to say we have a lot of clarifying questions, and then I feel like if folks want to start asking deeper questions too, I just want to make it through the clarifying questions. Did you have a? Okay, I have the list of clarifying questions, and then we can move on.
So question for Jack, you already hinted on this, but for this solid oxide approach, what's the preferred temperature range? Your comments seem to indicate pretty high temperature based on CSP, nuclear, etc.
Yes, the temperature range is between 600 and 800 Celsius. That's where you'd like to have the heat. Now, there are some technologies that are getting to lower temperatures, and we're working on some of those, but that's the temperature today.
That's a bit of a challenge in
Yes.
terms of materials. I know from my days running fossil programs at EPRI, so ultra supercritical materials, different kinds of steels and metal alloys. So there's more than just the challenge of the
I agree.
The electrolyzer itself.
And the solid oxide system itself has the same challenges because it's dealing with those same operating temperatures.
Ooh, dog.
Correct.
And then for Joe, one of the challenges we have on the NREL campus with our district heating system is the waste heat discharge from our high performance computer and data center coming out at a very low temperature, under 100 degrees Fahrenheit. What does your experience at Stanford or just your knowledge indicate for people who have that sort of low grade waste heat? What do you recommend that they do on it?
So I think you use your chilled water system to collect that heat. So in wintertime, when you have a net deficit of environmental heat, you need heat for your campus to the extent that you need it. You don't want to throw heat away even and get free air cooling. Now, if you already have a chilled water system deployed on campus, it's counterintuitive, but you tell the data center, look, I want you to use the chilled water system in winter so I can take your heat back to my central plant, use my heat pump to send it out to buildings that need it. I don't want you to use that free air cooling. They'll say, well, I don't want to pay for chilled water. I got an air cooling system here for free. So you work out a deal that says, all right, well, I'm not going to pay you. I'm not going to charge you to use the chilled water system because you could get rid of it cheaper, but it's worth it to me to collect it. So all during winter, we don't use outside air economizing anymore. We have a net deficit of heat. Let's stop throwing it away. Let's collect it because we already have a system to collect it called our chilled water system.
Right. Great, thank you.
So Jack, I had a quick question on you were talking about the feedstocks essentially being biodigesters as one example for renewable feedstock. I was just wondering if you had any other sort of ideas for a similar feedstock, just because you could imagine that might be a pretty limited feedstock when we're going toward 80%. But are there other things that you have in mind there?
I'm not quite sure what you're getting at there, except to note that for the idea of the carbonate reformer, electrolyzer, purifier, it requires something that can be reformed. And so that means you're talking about methane containing gases. Those are those biogases. That's why I mentioned those. But there could be other feedstocks that come from like biomass gasification and things like that also could work in this kind of a system. It just would require more heat input because you would, or less heat input, right? And you can't convert that heat because you can start from just pumping the CO2 out of it. Okay, so there are renewable feedstocks that include synthesis gases from biomass gasification and things like that too. That could be used. Those synthesis gases also can be used in these last steps here, right? In making liquid fuels using Fischer-Tropsch and things like that. Okay, so. And you're right about the amount of those resources not being sufficient for a large fraction of the fuels we need. But if we used them only judiciously, for example, only in aviation, using those liquid fuels, maybe it'd make a big dent. Yeah.
Okay, great. So I have a question for Joe and for Jack. So first I wanted to ask Joe, can we clone you and put you on various university campuses around the country? Okay, that's a joke, but
well, I
just wanted to say, yeah, I think it's great what you're doing, and but I do have a question, but I just wanted to mention that.
Sure. Well, I think you're right that there's a lot of resistance in conventional utilities leaders to embrace new concept and check them. They're all predisposed. And so that's that philosophical barrier, I think, a lot.
Yeah. Anyway, so but my question is, you said that you looked at a Northeastern campus and a few other campuses. You didn't mention which one, but maybe you can't. But I was just wondering, are those urban or rural campuses? And do you have any thoughts on different challenges?
I can mention that Midwest was the University of Illinois in Urbana-Champaign. They have a energy load about twice Stanford's. And they had some professors there that didn't want a new cogen plant, that wanted to see if a system like this would work. So we worked with them and their consultants to model it, and it will work. But they're so predisposed to cogen already in gas that for some reason their leadership just doesn't want to go through the life cycle cost analysis and other things. And I can't disclose it was MIT that we worked with. When the President's Council of Advisors came to see our system, Mark Gorenberg, one of your trustees, was on there, and he asked your president to look at a system like this because he knew the campus was in the midst. So tell your 10-year consultant worked, and then your new utility folks, think from Dartmouth or Brown or somewhere, came and spent a few days, and the system was modeled, and over 50% of the annual heat of MIT could be obtained through your own heat recovery, and then perhaps a great balance from ground. But
Does-
the challenge is we're working with Cambridge to put the pipes in the road, and these logistical things have led them to go with
Right.
cogen instead for now.
Right. Yeah, I mean, I think maybe the urban setting poses some challenges, and then also the age of buildings as well, right? I mean, when you did that work there, did you look at the current building stock on campus, or?
Yeah, so we have buildings not as old as, some of those in New England, and the older ones that have steam radiators throughout the building and stuff, we did convert some of those. That does take more work. And as far as an urban setting, Stanford's a fairly urban setting. It's high density, super high density utilities in the roads. So I don't, town and gown issues, I don't think it's an engineering challenge to find and route and put the pipes in, because we did it at Stanford fairly easily. It may be a town and gown issue, but I don't think it's an engineering or construction issue. The older buildings would take more conversion, though, than
Yeah.
newer buildings.
Right, okay. And then my question for Jack is, I was wondering, for the PEM and alkaline systems that you mentioned have been installed at the megawatt scale in Europe using
Yes.
renewables.
Yes.
Are those demonstration plants, and what kind of incentives were in place? Because I think it's interesting, there are a variety of low carbon technologies, nuclear, CCS in various locations where there are incentives for investment and adoption, and they're not taking off. In some places they are, in some places less so. And so I was just wondering, it's interesting to look at the incentives behind this.
It's mainly in Germany, and in Germany they have had a very big challenge in managing their grid, and in particular the northern wind power and transmitting that northern wind power to the south. And the idea there and the incentives that support it are to actually make hydrogen from the wind power primarily, and that's where these megawatt class electrolyzers are being installed. In the north, where there is more wind power, and then they're injecting it directly into the natural gas infrastructure up to, I think in Germany, it's a 6% limit. In other places in Europe, it's about 10% limit today.
Okay, but my question was the formulation of the incentive, was there an incentive to build a demonstration plant, or was there an incentive to solve a problem? I think to the point
Correct.
that Sonia made yesterday.
Many years ago, maybe 10 or so, they did the demonstration projects. Now these are actually just incentive-based, paid for by the incentives plus the costs of that they're recovering from producing the gas itself. So these are ongoing projects now that are paid for by the combination of incentives and value.
So the incentives are not specifically for electrolysis, for hydrogen production, or are they specifically for that?
I think they are specific
Okay,
for that.
that was my question.
Correct. I'm sorry, I didn't catch that correctly.
All right, one more clarifying question, then I have a list of folks who had their cards up for deeper questions.
Yeah, I'll try to be quick. So actually, Jack and I are involved in a project in the UC system to try to figure out what to do about the 6 cogen plants that system has and try to eliminate fossil emissions from those plants. So my question's for you, Joe. One of the things, and I'm not an expert, Jack is much more than an expert on this type of stuff, but one of the oppositions is that there's actually a big demand for steam on some of the campuses for things like autoclaves in the medical buildings. So I'm wondering how Stanford handled that. Do you still deliver steam at all or not?
Yeah, so the percentage of your total heat load for steam is pretty small, though. It's less than 5% on any of these campuses. And so we constructed a small unmanned steam plant using fluid boilers, and that's how we provide what we call process steam to the biomed-sci area that still needed it. There were technologies that could be converted, but they didn't want to convert some of them. Some would be more difficult to convert. But it's such a small percentage that you don't let that steer the design of the overall system. Likewise, in Stanford's new administrative campus, 1.5 million square feet we're building, since we can design for those buildings from the ground up, our consultants had an even better idea to build upon what we did. We have to supply 160 degree Fahrenheit hot water to an existing campus of various ages, because that's what the building interior zone reheat coils and stuff expect. But for a brand new campus, if you divorce your domestic heating hot water needs, and perhaps if you had any processed steam, take that 5% of the equation, realizing most of the heat's for space heating and air conditioning, tempering and so forth, We're going with a 110-degree hot water supply system on that campus, and the heat pumps draw about half the energy of the heat pumps at our campus, because you don't need 300-degree steam to heat a room, and you don't need 160-degree temperature water to make 72-degree air. 110's plenty with a proper heat exchanger. So that new Stanford campus will use what's essentially a chiller, just a slightly beefed up chiller with 0.7 kilowatt hours of input instead of 0.5 for a regular chiller. So our condenser water is 110 instead of the 95 you normally send to a cooling tower, and that'll do 95% of the heating load for the campus. And those small domestic hot water sources could be made either with electric heaters or small gas, and work on mitigating that small gas footprint.
Thanks.
All right, guys, so I have Paulina, Paul, Joan, Nate, Michael, Klaus, Dan, and James. I don't think we'll probably get to all of you, but if anyone wants to... 7 minutes. Okay.
Let's try to be really quick.
Okay, so combination of clarifying questions. So on the thermal storage, what are the temperature constraints? So Duquesne University in Pittsburgh in 2008 actually installed an ice storage for their cooling loads, but the heating loads were just, the heating pumps were not, maybe in 2008 things were different, but the heat pumps were not sufficient to meet their heating requirements. And I have heat pumps in my house, obviously very different than at a large scale, but I have to have a furnace for backup because at below 40 degrees, the heat pump does not operate in heating.
So for heat storage first, if you're on a steam system, it's impractical to try and store steam, right? So almost all district energy systems that are steam, they don't have a thermal energy component. They could use liquid salts or something super high temperature if they wanted, but they don't do it. When you convert to hot water, you save a whole lot on efficiency. You lose probably 15 to 20% of the energy between a central plant and buildings with a steam system. You're at under 4% with hot water. That being said, Ball State University in Indiana, many of you know, converted to ground source heat exchange for the bulk of their work, and it gets pretty cold there. So they use 150 degree Fahrenheit hot water supply for the campus, and they just keep it flowing all day. Stanford does aggressive night shutdown of buildings, and we reheat them back up in the morning to save energy. Ball State said, well, I could rip the guts out of all my building heat exchangers and upsize them or do what I got to do to be able to use 150 degrees to keep enough BTUs pumped through the building for this kind of weather. Instead, they just chose to keep the hot water flowing and the building warm all night, as it were, as their solution. So in cold climates, you could use any combination of re-engineering and building heat exchangers, higher hot water temperatures, or go with lower and just keep the BTUs flowing around the system constantly instead of shutting it off at night.
And then for the hydrogen, I guess a big question for me is why hydrogen? If we really think hydrogen is not going to be suitable directly for heavy duty transportation and jet fuels, and you're talking about these technologies, solid oxide and molten carbon, which are at the research stage. There's also some research to skip the hydrogen part, right? To go directly to the liquid hydrocarbons. So I guess my question is, why are we going back to hydrogen? Every 10 years.
Yeah, every 10 years back to hydrogen. So hydrogen has a couple of really nice features. At the end use, it produces no greenhouse gases and no criteria pollutants if you use it in a fuel cell or something like that. You also get higher energy conversion efficiency on that end use. So for example, using a fuel cell in a car, as opposed to using an IC engine in a car, you get an efficiency boost. And I know that Joan and Dan will talk about these conversion technologies for use in the transportation sector. It has higher energy density than does batteries. So hybrid battery hydrogen fuel cell systems could meet a whole bunch of additional transportation applications that are not easily amenable to batteries alone. And it's still zero emissions on end use. So there's a lot of applications in this last 20%, I think, that can use hydrogen. And then hydrogen is also the building block for a lot of these other possible fuel choices. So I think those are the main reasons why we would select hydrogen, but there are also these things like co-electrolysis or other means of producing, let's say, a hydrocarbon directly with otherwise captured CO2 and things like that too, that could play a role as well.
Great. So we'll talk more about this when Nate also gives his presentation. So I think maybe time for two more, Paul and Joan. I think you guys were the next to have your cards up.
Thanks. So Joe, letting the computer do the control is a great idea, but it's from things that I've seen in the UK, it's always the human element that ruins things. I've seen examples from my wife's work where people are turning on the heating because the air conditioning is getting things too cold. Do you have any provisions in the control system to note for sharp drops off in efficiency, such as would be, in that sort of stuff? And how do you?
Yes, indeed. So the software we developed has what's called persistence monitoring. So we store all the information about what the actual heating, cooling, and power loads on the system were, minute by minute, as it were. And what we do is at any increment we want, say at the end of a day or end of the month, we will ask the optimization model, given actual conditions of what actual energy prices were and what the loads were, run a dispatch and tell us, and then compare what the theoretical optimal dispatch would be to how it was dispatched. And let's see what the gap is. So with that, we hope to find out, within tolerance of forecasting, because the system uses weather downloads and forecasts every 15 minutes of prices and loads. So there's going to be imperfection there. You never get to theoretical perfection in hindsight. But once we train the system and see how close we can get and sustain actual operations to theoretical optimum, then with persistence monitoring, watch that. And if it starts to deviate, say if we were able to get within 3% of optimum, but we start to get to 4 or 5, we say, hey, what's going on? Are the operators turning the autopilot off and running the plant themselves and not following the computer's dispatch? Is our load forecasting gone awry? We have to adjust our algorithms. Is our market electricity forecasting gone awry? We have to adjust our algorithms. So we do have a persistence monitoring feature to keep the sails of the boat trimmed nice and tight.
Hi, I guess I'm up next. I had a question for Jack on the higher temperature electrolysis technologies, the solid oxide, the molten carbonate. Could you comment on how the interface works with that, with a variable renewable input, and what the turn down, kind of aspects of those, or load following, supply
Yeah,
following
that's a very good question, and one, it's a very active area of research, because these kinds of systems, if they're used as a 20% capacity factor or something like that, or have to ramp up and down and have to stay off for a week. But there are some ideas for active standby whereby you would, for example, produce 10% of electric power from these, for example, and keep the system warm and ready for electrolysis when you need it, when the need arises. Things like that are being investigated. They're not been proven yet. We've not built a system to actually manage that thermal management, which is a big concern for those high temperature systems over these dramatic and highly intermittent demand cycles.
So you are looking at things like reversible solid oxide systems.
Correct.
Kind of thing.
Yeah, it's one of the ideas for managing that downtime, whereas so that you could actually operate it in fuel cell mode and keep it warm.
Thanks.
Yeah.
Thank you, guys. Great place to end.